How are we doing? Doing all right. Any questions about anything before we keep going with the expectation? All right. Well, we talked last time about what we mean by expected value, just right off to the side here. So remember, so if your f of x is a PMF of a random variable, then the expected value of a function of the random variable, whatever the random variable happens to be, we do that by taking the sum over everything in the sample space of that function times f of x. So again, thinking of your probabilities as weights, this is a weighted average of whatever the outputs are of this function. Example I gave last time was if your homework counts for 10%, each exam counts for 20%. If you get 3 of those, and maybe your final exam counts for 30%, then your score on your homework will be multiplied by 0.1. Think about that as a probability. Your score on the exam 1 will be multiplied by 0.2. Exam 2 times 0.2, and so on down the line. So this is like a weighted average. Pardon me. You're weighting the average. You're weighting the outcomes of the function by whatever the probability of that outcome is. Okay. Now the examples that we did last time, we had explicit functions that we were using for our U of x, but it might be that we have maybe some information given to us in a problem, or if the function is not explicitly given to us as a formula. And we would still attack it the same way, and we'll see that in our next example. A couple of properties of expected value that we talked about last time were, if I had expected value of a constant, no matter what your probability distribution is, what is the expected value of a constant? Just the constant back out again, right? Because again, if you think about it in terms of this expected value formula, all you're doing is putting in the same constant here. I can think about popping it out in front. And all you're doing then is just summing up the probabilities over the entire sample space. And we know that sum always has to be what? 1. Good. All right, cool. You all have been paying attention. Fantastic. All right. So the other part that we talked about last time is that expectation is linear. So if I've got some constant a times a function u of x plus some other constant b times a function v of x, your expectation breaks up over the sum, and the constants pop out. So expectation plays nicely with respect to addition, so it also plays nicely with respect to subtraction, and scalar multiplication. It does not necessarily play nicely with respect to multiplication. Okay. Pardon me. Anyway, this type of property is called a linearity property. So expectation is linear. Anytime that it breaks up over sums and constants pulls out, that's a linear property. And for those of you who have had linear algebra or are taking linear algebra or will take linear algebra, you talk about linear transformations as well, and it has that same type of property. All right, anyway, so let's continue on, and then we're going to talk about a couple of special types of expectation today. So suppose we've got some random variable that's counting the number of days that a patient needs to be in the hospital. They give you this PMF. Notice in this case, it's not giving us a specific function that we're trying to do the expected value of. It gives us the function, but it's not an explicit formula for the function, right? It says the patient should get a $200 insurance company, $200 check from the insurance company each of the first 2 days they're in the hospital, and then a $100 check for each day after the first day. Okay. So notice that that's not a nice explicit formula that's given to us, but we can still do the same thing. Still use the same formula. We just need to just write it out rather than trying to make it as a nice fancy formula that we're selling. Okay. Well, given the PMF and given the support, how many things are going to be in your sum? How many things are we going to add together? 4, right? Because it says x is 1, 2, 3, 4, right? So I know that just from our expectation formula, I need to do something times f of 1 plus something times f of 2 plus something times f of 3 plus something times f of 4, right? Just from the expected value formula, I know I need to compute something that looks like this, right? Right? Function value times probability plus function value times probability all the way across. I just didn't write it as a nice, pretty summation formula. F of 1, and in this context, f of 1 represents what? We have probability of 1 day, right? This is probability of 2 days, 3 days, and 4 days, right? So what do you think needs to go in the blanks here? Then we're going to multiply by each of those probabilities. Yeah, how much money they get from in each day, right? So let's do the first one because it's probably the easiest of all 4. If the patient only stays in the hospital for 1 day, how much money do they get? 200. 200. Good. Okay. Right? If the patient stays in the hospital for 2 days, how much money do they get? 400, right? Because it says $200 each of the first 2 days, right? So I gotta make sure I do it twice, right? 3 days, how much do they get? 500. Good. And the last day, if they say 4, 600. Good. So that would be what we would need to multiply each of those by. Right, so each of the first 2 days, it goes up by 200. But if they stay longer than 2 days, they only get an extra 100 for each additional day. But the insurance company is still going to pay for the first 2 days. That's why we had to keep adding on, right? Is that okay? All right. So then to figure out these probabilities, f of 1 is equal to what? 4/10. Good. And f of 2 is 3/10. F of 3 is 2/10, and f of 4 is 1/10. Good. Whatever that number turns out to be. 80 plus 120 is 200 plus, pardon me. Pardon me. My goodness. Sorry about that. Plus another 100. Is that right? So 300 and then 60. Is that right? Did I do it right? 360? Did I add it right? 20 times 4 is 80. 40 times 3 is 120. 50 times 2 is 100. And 60 times 1 is 60. I think I added it right. Feels like I added it right. All right. I mean, this is a fairly simplistic example, but why would an insurance company might want to know such a thing? Yes, exactly. They need to know how much they need to charge for premiums, right? They're trying to make as much money as possible or save money as much money as possible, right? If this is what they expect out of each patient who enters the hospital, they need to be making sure that they take in enough money to cover this, right? If a patient goes in and this is the expected amount that particular patient is going to cost them, then they need to make sure they can cover it at the end, right? Insurance companies are like any other company. They're in it to make a profit, right? They're not doing it out of the goodness of their heart, unfortunately. Okay? They're in it to make a profit. So they're going to try to do calculations like this to try to figure out if something happens, what's it going to cost us on average, right? Because stuff happens, so they got to figure out how much it's going to cost. And then what's the likelihood of that? And that's what actuaries do from insurance actuary standpoint. They try to assess risks of events, how much it's going to cost if that risk happens, so then they can figure out what the premium needs to be to cover the losses they're going to have. Now, of course, then you get events like the fires in California, for example, which is going to cost billions of dollars, which they didn't expect. So be prepared for insurance premiums to go up, even though you didn't do anything. It's just a fact of life, because they're going to have to cover it, and so they're going to charge everybody. I mean, that is kind of the point of insurance, by the way. You've got a whole large block of people helping to pay for the few when something actually happens. That's what insurance is about. So you hear people screaming about can't have universal health care because that's socialism. All insurance is socialism. Everybody's paying for a few when it happens. All insurance is socialism. Just some people make a profit off of it. Anyway, I'll get off that soapbox. So anyway, is this okay? All right. In any event, this is how we do expectations. So in the next section, we're going to do a couple of special types of expectation. We've already talked about one of them, the expected value or the mean of the distribution. Another one that we're going to talk about is known as the variance of the distribution. All right, so let me switch pages here. All right, so let's ignore variance for the first part, for the time being, and let's do the mean for these different distributions. We already know how to do the mean. Mean is just the expected value of x. A lot of times you will see the Greek letter mu to denote mean. So if you see a mu, we mean mean, and we mean expected value. Mean is your first idea of average, right? Add them up, divide by how many there are. That's what you think of average, right? Mean is, in a probabilistic sense, weighted average, because we weight it by the probabilities. But if everything's equally weighted, then it's just the mean like you're used to. So for example, we'll go through the formula, but are each of these values equally weighted? Given what we're looking at the probability mass function, are they all equally weighted? Yeah. If they're all equally weighted, then I can figure out the mean by just how you always average them, right? And this was pretty straightforward. What is the mean? You should be able to look at that data set and tell me what the mean is. It's 15. Yeah. I'm not doing work, right? We can go through the formula and verify that we get 15 for part A. According to our expected value formula, remember again, this is add up everything over the sample space of just x times f of x. That's the definition of expected value of x, right? In this case, our x's go from 5 to 25. I'll write it a little bit differently, because notice they go up by the same amount each time. 5 times 1 times 2 times 3 times 4 times 5, just so I can see what the formula looks like. So I can write this as, I'll write it as x equals 1 to 5 of 5x times a fifth, right? And then your 5s will cancel, and if you add x from 1 to 5, you will get 15. I just did it that way to write it as a formula. I could have written it out longhand like we did the previous example as well, right? We could have done 1/5 times 5 plus 1/5 times 10, 1/5 times 15 times 20, 20, 25, and add them together. You still would have got 15, which is what we said we should have got, right? Okay. Pardon me. Sorry. So what about part B? Well, that one says that there's not a lot of work to do on that one either. There's exactly 1 point in your distribution. So what's the mean going to be? 5. Yeah, there's not a lot to do, right? So part B, there's only one term in your sum. You would do 1 times 5, right? So for B, if I just wrote it out that way, your mu would just be 1. Well, I'll write it the other way around. Usually where it is x times f of x. 5 for the x value, 1 for the probability, right? Pretty straightforward, I hope. Okay. The last one actually is a little bit of work to do. All right. So our mean here will add from 1 to 3. I could use formulas. We talked about a couple of different formulas before for adding up the sum of the first n integers or the sum of the first squares, sum of the squares of the first n integers. I'm trying to say that backwards. This one's probably just as easy just to plug them in, right? I've got 3 whole terms, right? Plug in 1, plug in 2, plug in 3, see what you get. So 1 times 4 minus 1 over 6 plus 2 times 4 minus 2 over 6, 3 times 4 minus 3 over 6. What do we get? That's a half, right? That is 1/3 times 2, so we get 2/3, and that is another 1/2. So we get 5/3 when we're done. Notice in the first 2 examples, your mean was right in the middle of your distribution, right? I mean, the second one is only 1 point in your distribution, so it has to be the middle. But in the first one, pardon me, in the first one, your mean is right directly in the middle, right? It's at 15, and there's equal things on the other sides. In this one, it's not right in the middle. 2's in the middle, right? And we are on either side of it. If we look at we talked about doing the bar graph last time, or a histogram, either or. We talked about this last time. And you can kind of see why from the distribution, what might be going on with the mean. Well, notice your probabilities are, what did we say? That one is a half, and that one was a third, and that one was a sixth. So, if this is if I go up by a sixth each time, I get 1/6, 2/6, 3/6, right? So I'd have a half would be that one, a third would be that one, a sixth would be that one. And I see that it's shifted on this side, right? It's stacked more towards the front. So I would expect that the mean would be moved over to the left. Right from the middle. Does that make sense? Because it's more, you're going to get a lot more 1s than you're going to be getting 3s. So when you average them all out, it won't hit this middle term. It'll be over here a little bit to the left. Okay. That okay? All right. So I'm talking a little bit about where that mean got shifted a little bit for this type of a distribution. So we might want to start to get some measures of things like how spread out are things, or how are things shifted. Okay? So that's what we're going to talk about today, with some special expected values besides the mean that tell us a couple of those things. That tell us how to calculate things that give us an information about how spread out things are, or how messed up the distribution might be from a skewed standpoint. So that's the idea of, well, the first part with the spread is the idea of variance. So notice that if you had, sorry, goodness. If you had a distribution like the first one, where you had your bar graph was 5, 10, 15, 20, 25, and then everything was at a height of 1/5, right? That looked like that. Versus if I did same support, same possibilities for plugging in for x, but I made something go up by 11ths instead, just so that the numbers add up to 1, and went 1, 2, I think 11 works. I may have added wrong. 6, oh, maybe it's 9ths. Sorry. Doesn't matter. I wanted to add it to 1, so let's make sure I have the right numbers. Something looks like that. So 1 9, 2 9, 3 9, that gives me 6, 8, 9, I have every 9 and not 11. Now that I added it. That mean should also be 15. I can tell that it should be 15 because notice my distribution here is symmetric about this middle point, right? There's as many, if you think about doing this over and over and over and over again, that's the idea of expected value. On average, you should see as many 10s as 20s, and you should see as many 5s as 25s, and those will average out to 15, right? But notice that there's a difference in the spread here. What I mean by that is, if I do this experiment, this first experiment, over and over and over and over again, I would expect to see an equal number of 5s, 10s, 15s, 20s, and 25s, roughly speaking, right? Okay? Would the same thing happen for the second distribution? No, I should see 3 times as many 15s as I do 5s, for example. All right? So I'm going to be bunched more up in the middle than out on the sides. So this distribution should have a bigger spread than this distribution does. If you just think about from data points perspective, right? If you think about piling them up. Okay? So we want a measure that describes that, and that's where variance is going to come in. So when I'm talking about spread, I'm looking at how, if I think about, I kind of want my mean to be in the middle, although going forward in statistics, you talk about different ideas of middle, but for right now, let's think about the mean being in the middle. If I want to talk about spread, I want to know on average, how far is anything from the middle point? That's the idea. Okay? So if you want to do how far something is from the middle point, the mean, then we calculate what's referred to as a deviation. And it's just the data point minus the mean. That's what a deviation is. Now, if you've done standard deviation before, it's related. But this is what we mean by a deviation. Okay? It's just how far is something from the mean. If x is bigger than the mean, it's a positive deviation. If x is less than the mean, it's a negative deviation. Now, again, if we want to calculate something on average, how far something is from the mean, you might want to think of, okay, I'm going to average up these deviations. That's a natural thing to want to do. Average up the deviations, see what happens. Expected value, again, for us is average, right? It's a weighted average, okay? So one thing you might try, it's a natural thing to try. Do the expected value of x minus mu. It's a natural thing to try, right? If I want to know how far on average everything in my support is from the mean, I do a weighted average, so we do expected value, right? I do a weighted average of these deviations. Now, what did we say that we had for expected value with respect to differences? What can I do with that expected value in that difference? Split it, right? So I can write this as expected value of x minus expected value of mu. Now, what's another name for expected value of x? Mu. And what did we say was an expected value? And mu is now a constant. And what did we say the expected value of a constant was? The constant. So what do we end up with here? 0. Yeah. That's a terrible measure for spread, right? This says, hey, there is no spread no matter the distribution, which clearly that's false, right? Now, of the distributions that we did to start with, there is one that has no spread. If A, B, and C, which one has no spread? B. There was only one data point, right? that is the only distribution that you have that has no spread. It's a 1-point distribution, which is exceptionally uninteresting and you're never going to study it. Okay? Okay. All right. So any other distribution that has more than one data point to it is going to have some spread to it. That's a terrible measure of spread, though, right? I mean, it would be easy, but it'd be terrible, okay? However, if you're, none of you are going to do this, but if you are calculating standard deviation by hand, this is always a good check to make sure you're doing it correctly. Add up your deviations and see that you get 0. That should happen for any data set, by the way. If you're doing a sample and want to calculate standard deviation, and you do the sum of the deviations, you should always get 0 every single time. So it is a nice check. It's just a terrible measure. Okay. So what do we do instead? Well, here's the problem. The problem is that we've got some positives and we've got some negatives, and they can't end up canceling each other out, right? So there are 2 hopefully natural operations that you could do to that deviation that would allow you to change negatives into positives. What are 2 things that you can think of, 2 operations that you could do to that would change a negative to a positive? Absolute value is one. Great. What's the other? Squaring does it pretty quickly, right? Okay. So there's actually applications of both of those things. But thinking from a calculus perspective, which one of those is bad with respect to derivatives? Squaring or absolute value? Absolute value. So we're not going to use absolute value. We're going to square instead. Okay. But there are reasons why you might want to do absolute value. And there is a measure in statistics. It's called the mean absolute deviation. And you would work at absolute values versus square. Okay? So just know that there are applications for the absolute value. But for our definitions or variance, we're going to do the squaring instead because it behaves more nicely with respect to calculus. Okay? All right. So this is how we're going to define our variance of a distribution. Oops. So variance of a random variable. We denote variance with a sigma squared, a small letter sigma squared. Pardon me, goodness gracious, I apologize. This is the expected value of the square of the deviations. Okay. This is, now keep in mind, this is the definition. And you should absolutely have the definition in your brain. Okay? This is not typically how we calculate variance. Okay? But this is, we're going to do it a little bit of a shortcut method to do it. But this is the definition. Okay? So just know that this is the definition. It's the expected value of the square of the deviations. Okay? So let's do this using an example, and then we'll talk about how we do this a little bit more easily, if you will. So just to make it a little bit more, well, I'll do the first one. The second one's not anything. It's just 0. Okay? All right. So for the first one, again, the probability was 1/5 for every single possibility, right? So your expected value of x minus, we said that the mean in this case was what? 15? Right? So it's x minus 15 squared. Pardon me. So I'm just going to, rather than making out a formula for it, I'm just going to write it out longhand, okay? Because there's only 5 terms, right? So we would have 5 minus 15 squared times a fifth plus 10 minus 15 squared times a fifth, 15 minus 15 squared times a fifth, 20 minus 15 squared times a fifth, and finally 25 minus 15 squared times a fifth. That's the definition, right? You plug in the x value and multiply by the probability that that x value happens. and do that all the way across. There were only 5 terms, so I just wrote out the sum longhand. Oh, what do you get? You get a fifth times, what is that, 100 plus 25 plus 25 plus 100? Yeah, 100, right? So, what is that, 250, so 50? Did I do it right? I was just blindly trusting my arithmetic. You should absolutely not do that. Okay. Just for verification that this really is giving us a different measure of an idea of the spread of the distribution. Let's go, rather than doing part C, let me go back up and do this other distribution that we agreed that the mean was the same, right? We said both of the means had 15. Over here, you would do the exact same sum that we just did in the previous example, except that our probabilities will now be 1/9, 2/9, 3/9, 2/9, 1/9, right? So this will be, if I do the variance here, you would have, I'll just write it as negative 10 squared times a ninth, negative 5 squared times 2/9, 0 squared times 3/9, 5 squared times 2/9, 10 squared times 1/9. We see where the negative 10, 5, 0, 5, 10 are coming from, just the subtract. It's the same subtractions, right? So what do we get here? You get 100 over 9, and you get 50 over 9, and same here, and same here. But rather than dividing that, notice that that's still 100 and 50 and 50 and 100 like the previous one, except that now we're dividing it by 9, right? So you get 250 over 9. So we get 300. So what was the original? Well, the other ones were 25, weren't they? Yes, that was my problem. Sorry. Not 250, it's 300 over 9. Thanks. So 100 over 3. Anyway, that's 33 1/3. See, I told you don't trust my arithmetic. Which is definitely less than the other variance, right? So again, this is giving us a measure of spread. We said if we were thinking about doing the experiment over and over and over and over and over and over again, we would expect that there's going to be a lot more 15s than 10s and 20s and then 5s and 25s, versus in the first one, we'd have an equal number of them all. So it'll be more spread out. Okay. So that's what the variance is designed to do. It's giving us a measure of spread. The lower the variance, the lower the spread. Higher the variance, the larger the spread. Okay. All right. Questions on that at all? Okay. I promised that we don't typically do variance in this fashion. We usually do a slightly different computation. So let's just think about how we can simplify this. Now, we said that expected value does not behave nicely with respect to products. So I can't just take the squaring and pull it out. That's not allowed. Okay. However, pardon me. However, we can FOIL. All right, I can multiply on the inside. What do you get when you multiply out the inside? Good. Yep, exactly right. And now, do I have a sum and a difference? So how can I rewrite the right-hand side now? Good. Good. All right. So Austin did a couple of steps at once, which is perfectly fine. We can break up the expected value over this difference in the sum, and you can pull out the constants. The 2 is a constant, and the mu is a constant. So I can pull out the 2 mu, and on the end, mu squared is a constant, so the expected value of the constant is the constant. We okay with that step? Cool. What's another name for E of x? Mu, yeah. So I get minus 2 mu squared plus a mu squared, right? So I can simplify this a little bit more. So we can do expected value of x squared minus mu squared. But we just said a second ago that mu squared is the same, or mu is the same thing as expected value of x. So it's kind of a nice little symmetric formula there for it, right? Expected value of x squared minus expected value of x quantity squared. And this is typically, not always, okay? This is typically how you'll calculate variance if you're doing it from a probability mass function. Not all the time. We will see a specific case where we'll do it slightly differently, okay? I mean, it's a variant of this, but it'll be slightly differently. All right. So let's see if we can do the next example here and then put this formula to use, okay? All right. Pardon me. I copied this out of another textbook, and you can tell the page was bent when I made the copy, so that's why it kind of goes up. I left it because it looks funny. So, all right. Another reason why I like this particular problem is because this textbook uses a smiley face for a variable. So, all right. This one asks us to calculate the mean age. We're also going to do the variance as well. So we're going to do mean and variance here. Doesn't matter what the particular numbers are. We just want to do it. Before I do mean and before I do variance, what do I need to figure out? I need to figure out what smiley face is, right? How do I figure out what smiley face is? Yeah, 1 minus the sum of the other ones, right? That's exactly right. So our smiley, that's what we need to do first. We need to figure out what the smiley face is. By the way, I'm a big fan of creative variables. So if you want to amuse me on your homework, please put some creative variables in there. It always makes me laugh. So this will be 1 minus 0.16 plus 0.42 plus 0.1 plus 0.28. What do we get? 586886 or 9. So was it 0.04? Did I do my arithmetic right? 58, 68, 96. Yeah, so it's 0.04. Okay. All right. So now we want to do the mean. What calculation do we need to do to calculate the mean? Okay, so it's z of x. So how do we calculate that? Yep, sorry. I was actually asking for the computations. Sorry. Just, yeah, well, let's just write it out longhand. Yeah.
32 times 0.16.
Good.
39 times 0.04.
Good.
45 times 0.42.
Good.
57 times 0.1.
Okay.
62 times 0.28.
Good. Yeah. You said 8 and I wrote a 5. I have no idea why. You said 8, I wrote 5. Yeah. So again, x value times the probability of that x value happens. So here in the table, I'm just multiplying basically straight down columns, right? And I add them together. Do we get a value for that? Because I'm not doing that one in my head. $48.64. Okay. That okay? All right. So when we want to do the variance now, let's do it with the, rather than doing the x minus mu squared formula, let's use the formula we just came up with, right? Because we already figured out that part, didn't we? We already figured out that expected value of x part. So let's do expected value of x squared Now, we already have the sum written out longhand here for mu. What change do you need to make to that sum to get this expected value of x squared? What do I need to do? Just square the x values, right? Right? This says do the x value, square it, and then multiply by the probabilities, right? So I need to square 32, square 39, square 45, and so on down the line. So this will be the x value squared times 0.16, so 32 squared times 0.16, 39 squared, times 0.04, 45 squared times 0.42, 57 squared times 0.1, and 62 squared times 0.28. That makes sense where that's coming from? I hear lots of tapping, so get a value from somebody, I'm sure.
2,476.4.
Is that the variance? No, that the value is, and be careful with that. That's a common mistake that gets made is you'll do expected value of x squared and think you're done. That's not the variance in this case. To find the variance, remember it's expected value of x squared minus expected value of x quantity squared, right? So you'll do 20, good Lord, whatever that number is, 2476.4 minus 48.64 squared. Did you get a value for that?
110.55.
Okay, cool. So that would be your variance in that case. Is that okay? Not too bad? All right. Let's look at the next one, since we're having so much fun. Yeah.
If you took the square root of that and just had sigma.
Yep. That's standard deviation. Yeah. So that is another measure that we do. So a lot of times you'll see standard deviation versus the variance. That sigma value is the standard deviation of the actual distribution, the population. If you had a sample from a population and you compute the standard deviation slightly differently because of the fact that you're doing a sample rather than doing the population. And so it's a slightly different, it's a slightly bigger number because you lose some information if you're taking something from a sample. And so that's actually a statistics question. It's a very good question. But yeah, you get standard deviation. And again, pardon me, I don't know why I'm so phlegmy today. I apologize. The standard deviation kind of undoes that, or excuse me, the squaring, and the square rooting kind of undoes the squaring that we did in some sense. So that standard deviation is kind of your measure of how far on average things are from the mean. Not quite, because you squared and then added, and then you're doing a square root, so you're not really undoing the squaring quite. But in some sense, that's what you're doing, is undoing the squaring with that. My goodness. Sorry. All right, let's look at this one. This one's just asking for expected payment. This one looks a lot like that problem we did a minute ago with the hospital stays. So we're going to have 5 terms in our sum. If we want expected payment, what do your 5 terms in your sum look like? Good. Good. And the last 2 values will be 350? Because it's $50 per day after the 3rd day. 6 minus 4 over 15. And the last one be 400 times 6 minus 5 over 15. I hear some tapping, so wait for the number here. $220. Okay, good. There we go. All right. Again, here, if you wanted to do variance, what would you calculate first? If I asked you to do the variance on this one, what would you do first? Yeah, you do that expected e of x squared piece, right? So, oops. And the only thing that would change in your sum would be what? Good, exactly right. Squares on the payment amounts, right? Do 100 squared, 200 squared, 300 squared, 350 squared, 400 squared. So you'd have 100 squared times, how is that, 5/15? So that's a third. And you'd have 200 squared times 4/15, and 300 squared times a fifth, and 350 squared times 2/15, and 400 squared times 1/15. And if you got calculators, either, or you can just go grab the previous entry by doing second enter, and it'll bring up the previous entry, or go up in your screen with your arrow key and grab it and bring it down. It's good stuff just to insert the squares, right? So you have to retype it all. Even? Okay. All right, and so then the variance would be what? What would we do to calculate the variance? 59,000 minus 220 squared. Good, exactly right. 59,000 minus the 220 squared. Okay. Cool. Does that make sense? All right. Now, just to mention this because it's a good indication that you may have done something wrong along the way. Remember, I told you, even though we typically don't calculate variance in this fashion, this is your definition of variance. Can that ever be negative? No. Think about how expected value is calculated. It's a sum, so you're not subtracting anything, of function times probability. Can this function be negative ever? No, we're squaring. Can probability be negative ever? No. Okay? You're adding a bunch of positive things, so it has to be positive. It can never be negative. Okay? So if you come across a problem you're doing, you get a variance as -5, you've done an arithmetic error somewhere. Okay? it's a good indication you've made a mistake somewhere, right? So even though we typically do variance, my magnet was really strong that time. We typically do variance using this formula, which has subtraction in it, right? Remember, the definition is this. That can't be negative, so this subtraction can never be negative. Okay. Again, like I said, it's a good indication that you may have done a calculation incorrectly. If you get a, well, you definitely have done a calculation incorrectly somewhere if you get a negative value for variance. Okay. There's not a good indication. It's a no, you screwed up. Okay. All right. Any questions on that one at all? Let's see what we got else we got on here. All right. So this one is going to introduce one of our special types of distributions. We're going to have several of them as we go along. Some of them will be discrete. Some of them will be continuous. This one is what's referred to as a geometric distribution. I told you a little while ago that we'll have some PMFs that will have an infinite support. And when you talk about geometric series, when we did a couple of those, this is where geometric distribution and geometric series, same kind of idea. All right, so we're going to flip a coin until we see the first head. This one wants to, X is going to count the number of flips before the first head appears. I'm going to change that slightly. I'm going to say the number of flips. I'm going to change it from before to until the first head appears. It's not going to change too much with regard to the expected value, because if you know the expected value, expected number of flips before the first head appears, you just have to add 1, and that's the expected value of when it appears until, right? Okay. So let's think about it. Let's think about writing it out, and then think about what it'll look like as kind of a function, and then we can check that it really is a PMF, and then we will calculate expected value, and we'll calculate the variance. Okay? Sound like fun? No? Okay, that's fine. We're still going to do it. All right. So this is talking about flipping heads, but let's see if we can do it a little bit more generally than just heads or tails, because that probability is a half all the time, right? The same scenario will work as long as you've got something that you're looking for happening versus not happening. Typically, happening we think of as success, not happening as failure. So you've got 2 possible outcomes. A lot of times, and the probability that it happens if you do it over and over again doesn't change. And one outcome doesn't affect the next outcome, right? So if you flip a coin, the probability of getting ahead doesn't change from time to time, right? And it certainly doesn't matter if you flip 10 heads in a row, it's still 1/2 that you'll get ahead the next time, right? So they are identical, independent trials. We refer to those as Bernoulli trials, and we'll talk a little bit more about that in another section. But they're independent and identical. That's the important part, okay? All right. So let's let P represent the probability of success. Oops. What would be the probability of failure then? Yeah, and so what would be the complement of P? 1 minus P, right? Because if P is the number, right? So if P is the number that represents the probability of success, then 1 minus P, and sometimes it's referred to as Q, is the probability of failure. All right, let's do it step by step, and then see if we can come up with a general formula for the PMF. What's your lowest number of trials that you can have until you see the first head in this case? 1, right? So X would be the smallest thing would be 1, right? It could be 2, it could be 3, it could be 4, and so on down the line, right? All right. So if X is counting, let me write this down. Let X count the number of trials until the first success. Oops. What would it be in this case? Well, it would, for the heads, it'd be 1/2. So for a general P, it would be, if P is probability of success, and it's 1 trial until you see success, it's going to be P. Yeah, good. Yeah, it'll just be P. For this specific example with the heads, it would be 1/2, right? But generally speaking, if I'm letting P represent the probability of success, success on the first trial is just P. Okay? Now again, X is counting the number of trials until the first success. So if X is 2, what happened on the first trial? Failure. So what's the probability of seeing failure on the first trial and success on the second trial? Yeah, Q times P. Or I'll write it as 1 minus P times P, right? Yeah. Okay. What about 3? Yeah. It has to be failure, failure, success, right? Four trials. Q cubed, good. All right, do we have the idea? Can I do the general? Can I say probability that capital X equals little x? What's going on with your exponent? It's x minus 1. Good. So this will be q to the x minus 1 times p, or 1 minus p to the x minus 1 times p. So for a geometric distribution, your PMF is 1 minus p to the x minus 1 times p, and your support is 1, 2, 3, and so on. Okay, so I said that I want to do 3 things with this problem. Verify it's a PMF, find its mean, find its variance. We're going to do this for pretty much any distribution that we come across. We're going to write down what its PMF is. We're going to write down what its mean is. We're going to write down what its variance is. And then there's one more thing that we're going to write down that we'll talk about at a later time. Okay? Because the idea behind this is, given a scenario, recognize what kind of distribution it is and get its important information quickly. Right? So that's why I want to write these things down and collect them. And yes, I'm going to expect you to memorize them. So just to give a little precursor. Okay? I know I'm mean. I'm terrible. Okay. All right. In any event, let's check that this really is a PMF. If I want to check this as a PMF, I have to show that if I add up the function over the support, I get 1. Right? That's what we have to show. And maybe now you can see why we call this a geometric distribution, because this looks like a geometric series, right? Okay. All right, so pop the P out in front. Oh, for heaven's sake. Keep shifting on me.
And then I said, I personally like, you can do it however you want. I don't really care as long as it's right. I personally like writing my sum to start at 0 and my exponent to be just an n for my geometric series, because then my formula is like that, right? That's how I personally like to remember the formula. Okay. To do that in this case, I need to re-index my series to start at 0. If I take my x down by 1, I've got to move this x up by 1, right? Okay. Pardon me. Yeah. Okay. And now I can use my formula. So my R value here is 1 minus P. Something goofy is going on. Where have I made my error? I made an error somewhere along the line here. Because I'm getting 1, which shouldn't happen. Oh no, I should get 1. Duh. I'm not doing mean yet. Sorry. My brain was thinking about, I was thinking ahead. Sorry. Yeah, 1 over 1 minus P, 1 over 1 minus the quantity 1 minus P. I was thinking I was doing expected value. I'm like, I'm not supposed to get 1. No, I wanted to show that it actually equals 1, which is what we're getting, right? The denominator simplifies just P, and so we really do get 1. We really do get a PMF here. Okay. All right. Expected value. Sorry, my brain died on me. It happens. It's okay. All right. Expected value now. It's a similar sum, except that now I need to put an x out in front. Right? Yeah. Okay. Still can pop the P out. And now, hopefully, this looks like something we did a little bit ago. Remind you of a calculus thing. What does it look like we did to the inside? It looks like a derivative, doesn't it? And we talked about that a little bit, that if you differentiate power series, you still get a power series, right? So remember that over here, if I think about from a derivative standpoint, we get that, don't we? Agreed? Okay. So now notice that this is set up exactly like this is now. Yeah? Oops, not. This is just times 1 over 1 minus P squared. And we get 1 over P. So for any geometric series, any geometric distribution, the mean is 1 over the probability of success. So if you're flipping a coin, how many trials on average do you think you'll see before you see the first hit? 2, 1 over a half, which kind of makes sense, right? Or if you think about rolling a die, if you think on average how many times you have to roll the die before you see a 6, it should be 6, because the probability of rolling a 6 is 1/6. So it kind of makes sense if you think about it for a geometric distribution. So its mean is just 1 over the probability of success. All right, let's do variance. Variance is a little trickier. Remember I said typically we do variance by that expected value of x squared minus expected value of x quantity squared. This is one of those times that that's not the most convenient one. Okay? Yeah.
So like with your example with the heads, would it be exactly 2 or would it be 1 and 2? Because you'd be able to get like 4 or 5 would be first.
Well, just be, but there will also be a lot of times that you'll get it on the first try. So it's averaging out to 2.
So it'll average out to exactly 2.
Yeah, I mean, if you can do it infinitely many times, yes, it'll average out to exactly 2. But you can't do it exactly. You can't do it infinitely many times, but it should be close to 2. It won't be. Typically, it won't be exactly 2. It'll be really darn close, though. Sometimes it might be exactly 2, depending on how many trials you do, but it should be essentially 2. Okay. All right, so there is another little trick that we can do to help us calculate variance. And that's, instead of doing expected value of x squared, we can do expected value of x times x minus 1. Because this is the same thing as, this can help us with the formula, and then we'll see why we want to do this here in a minute. That's that, isn't it? Okay. And then I can split it up over the sum, or the difference, I should say. All right. So, looking at this formula, what would I need to do to this formula to get the formula for the variance? If I look at what I just did for this, what do I need to do to this to get what I actually want for the variance? Or what I need to do? I gotta add something back and to do a subtraction, right? I've got to remember your formula for expected value of your formula for variance is that, isn't it? What do I need to do to this to make it look like that? I got to add back in expected value of x and subtract the expected value of x squared, don't I? Okay. So this is going to be the same thing as expected value of x times x minus 1. And then add the expected value of x and subtract the expected value of x squared. Okay. It looks complicated, but it's going to be a lot easier to do it for this particular example than trying to do it with the other formula. Here's why. Expected value of x times x minus 1 Oops. So same idea, except I'm going to take the PMF and multiply it by x times x minus 1. What do you get in that sum when you plug in 1? What do you definitely get in that sum when you plug in 1? 0, because x minus 1 is going to kill it off, right? So rather than rewriting it, I'm just going to subtract the 1, make it a 2. Doesn't change anything, right? We agree? Okay. I'm going to scroll back up for a second. How did we get from this to this? Derivative, right? Took the derivative with respect to r in this case, right? Okay. Do it again. What do you get for your series? On the left-hand side, what do you get for the series? We'll start at 2. And what comes down in front? Yep, the n minus 1 comes down, and the power becomes n minus 2, right? Differentiate the right-hand side, you'll get a 2 over 1 minus r cubed. The 2 comes from the fact that I've got that 2 exponent there. Yeah. Okay. Why did I do that? Because I'm mean? Yeah, maybe. Why did I do that? Let's scroll back down. I have x, and I've got x minus 1. Makes you look like a second derivative, doesn't it? That I just did? What does this exponent need to be? X minus 2, right? Okay. So I'll pull off a 1 minus p and make it an x minus 2. Okay. So we'll take out a p
and a 1 minus p. And now I can use the formula we just came up with to get p times 1 minus p from the out in front. It was 2 over 1 minus r quantity cubed, right? 1 minus p just becomes p. So I got p over p cubed. So this becomes 2 times 1 minus p over p squared. We're almost done. And I know you're all hating it. That's too bad. I love it. So we're doing it anyway. It's very algebraic. It's fun. I like it. So we're doing it. Okay. You don't have to reproduce it, but you need to know where things come from. It's important. Okay. All right. So we just said a minute ago we can do variance by expected value of x times x minus 1, which we just did, right? Add back the expected value and subtract off the expected value squared. We just calculated e of x times x minus 1. Add back 1 over p, we just found that a second ago, and subtract 1 over p squared. The square of 1 over p, right? Because we did 1 over p earlier, didn't we? Yeah. If we factor, rather than getting a common denominator, I'm just going to factor out 1 over p squared. I get 2 times 1 minus p on the first term. On the last term, you'll get a minus 1. I didn't have a p squared in the denominator here. So if I pull out 1 minus p squared, or excuse me, 1 over p squared, it'll leave a p. And if you simplify all of that, I've got 2 minus 1 is 1, minus 2p plus p is 1 minus p. So I get 1 minus p over p squared, or if you prefer, that's q over p squared, right? In this case, that's the variance. Okay. It turned out nice. Even though it was ugly to get there, it turned out nice, right? Okay, you don't care. That's perfectly fine. You don't have to care. All right. Anyway, like I said, it's important to know means and variances of these different types of distributions because we will want to be able to do them later. All right. I got an assignment here for you. Doing expected value stuff. Please write your answers on separate paper. Don't write it on here. I don't want you to try to read it on here. Oh, you already heard that speech in here. Thank you. We're gonna run out. All right. Have a good one. This will be due when you take your test. You got a test next Thursday, right? It's very exciting. This will be due on Thursday with your test. We'll talk more about these expected value things next time. I'll get some review problems posted on Moodle as well. Okay, so you can have those to work on. We'll do some more stuff on Tuesday and talk a little bit about the exam. All right. Have a good one. We'll see you.